jumping, and I made a simulation about it. Well, because we recognized that there were two interactions involved in the jump. One is gravitational interaction, and one is elastic interaction from the cord, from the bungee cord. And well, they happen to be both happen to be conservative. So now we have, I mean, a lot of possibilities of how we want to relate motion with interaction. We could think about kinetic energy of the jumper and then calculate work. And calculating work would be easy, because if we have a concept of potential energy, we really don't need to integrate force in order to find work. We can just calculate difference in potential energy at one location and another location for both interactions, and this gives us work done. Well, we could put one of the conservative interaction, we could recognize that it's conservative interaction, therefore we could combine it with kinetic energy to make it mechanical energy, and we could put either one or two. Well, if we put just one, so let's say that we put elastic interaction as a conservative interaction, then we will relate work performed due to gravity with the change in mechanical energy, which involves elastic potential energy and kinetic energy. We could do it the other way. We could include gravitational potential energy combine it with kinetic energy and say that this is mechanical energy, and then have elastic work as a non-conservative work. This is why I actually prefer to say that in the second version of work energy theorem, that we have work not included in the potential energy rather than non-conservative work, because sometimes we can make a mistake and not recognize that a certain interaction is conservative interaction. We could also actually put both interactions on the side of kinetic energy, recognizing that they are both conservative, and therefore non-conservative work would be zero, correct, and mechanical energy would be conserved. Well, if mechanical energy would be conserved, and this is how the jump would look like. Yeah, so for example, I assume that this jumper has a mass of 100 kilograms, that the spring constant is 20 newtons per meter, and if the person jumps, I mean, over here you will see plots of kinetic energy, gravitational potential energy, elastic potential energy, and I think combined or whatever. I mean, let's see what I forgot. All right, let's stop at this point. Now let's analyze now the graphs. So that blue line represents kinetic energy. At the top of the platform, the person did not move. Kinetic energy of this person was zero. Now, as the person was getting lower and lower, kinetic energy is increasing. Well, and eventually, when the cord is going to slow down the person, kinetic energy drops. Now let's see about the work of potential energy. So gravitational potential energy now is a linear function of position. Where did I pick a reference for gravitational potential energy consistently with this drawing? Yes? Up at the very top. I assume that up at the very top both potential energies are zero. So well, the cord is relaxed. So it is convenient to choose that state of the spring as the reference for potential energy. Therefore, for the cord, it's the same thing. And, well, I can see that this cord has length of about 50 meters, because up to 50 meters, I see that potential energy associated with the stretch cord is not changed. It maintains zero, so the cord remains unstretched for the first 50 meters. And then it acts like a spring. So it's a quadratic function of the stretching of the cord. And gravitational potential energy is a linear function. That red line is a combined potential energy. Now, if you see what will happen if I add kinetic energy and potential energy at any instant, that sum is going to be zero, which means that which energy is zero all the time? Which one? Mechanical energy. Mechanical energy is preserved. And since I selected reference for potential energy over here, all the time mechanical energy is zero. Now that potential energy is negative all the time. Up to the point, because now let's go further and all right. At this point, I mean, the plots maybe are not too accurate, but I mean pretty close. Over here, what will be kinetic energy and potential energy at this point when the person stops? Should be zero, correct, right? Because now kinetic energy is zero. Mechanical energy is conserved, so it has to be zero. Therefore, potential energy also has to return to the zero value. All right, let's now see what will happen on the way back. All right, so now, as the person moves up, both spring and earth perform work. Spring now performs, it decreases its potential energy. Spring potential energy associated with the cord decreases, which means that the cord is performing positive work or negative work. If potential energy is decreasing associated with that interaction, recall that changing potential energy is opposite to the work. So if potential energy is decreasing, it means that this conservative interaction results in positive work, right? Yes, so potential energy of the cord is decreasing, the cord is performing positive work. Potential energy, gravitational potential energy is increasing, therefore the earth is performing negative work. Okay. Well, however, the net results, I mean, both together perform positive work, therefore kinetic energy is increasing. Now, so far we assume that there are no other interactions, so potential and mechanical energy is conserved. So all the time, the person has mechanical energy of zero. So how far the person is going to move up? To the point, well, when it stops, mechanical energy is going to be zero. So where is that point? Over there. Well, really, if this was, what we considered so far was reality, bungee jumping would be very dangerous. Because if mechanical energy were conserved, then every jump would end up that way. If you are lucky, you would maybe could maneuver your body in such a way that rather than hitting the ramp, you can jump on the ramp on that side. Now, how come that it doesn't happen like that? The energy gets transferred somewhere. The person has to lose his or her mechanical energy somewhere. How that person is going to do if energy is being conserved. Something has to perform negative work, correct. And that something is that we are flying in an air. So right now, I mean, you could actually see that I put here that there is no zero, that there is a zero resistance due to air. How about if we reset it? And now I'll put air resistance into it. Now think how air is going to so now air is air does air result in conservative work or not? Is it conservative interaction or not? It's not conservative. Prove it to me. And I tell you, give me, think about it. I mean, think about work done by air on me when I do something like this. I go to this side of the room, and now I will go back, and I'm here again. Give me now the argument that indeed air, this drag was not conservative interaction. Do I have a volunteer to say that? No? Yes, okay. I understand what you are saying. Additive, he was saying that in all cases I had to add, I mean the sign of the work was the same, right? So the work done by air was not zero. All right, now was it positive or negative then? Yeah, because JD came to the conclusion that it is not zero. But was it positive or negative? Well, think about when I walk this way. Does air perform positive work on me or negative work on me? I mean, if I walk with this speed, you can assume that it is almost zero. But however, if I move fast, the drag is substantial. And when you jump, you are getting relatively high speed, so that drag is substantial. All right, so let's figure out what were the directions of displacement and the force, which way I was moving. So if I'm walking that way, what is the direction of drag? That way, correct. Therefore, differential work, if I move just one step, differential work is going to be positive, or negative. Negative because, well, we take magnitude of the first vector times magnitude of the second vector times cosine of the angle between these two vectors. Cosine of 180 degrees is -1, so it's negative work. Along each of the differential displacements, when I walk in that direction, JD recognized that work was negative. Now when I turned back, the differential displacements are in this direction, but drag also changed the direction. So there is still 180 degrees angle. Cosine of 180 degrees is -1. So now I believe that the work performed by air was negative. So what? How does it prove that interaction was not conservative? Well, so far we checked only one path. What say?
You check a different path.
Okay, let's check different path. I will go behind the screen. And still negative. Well, so what? How does it prove that the interaction is not conservative? Consult with each other. How does it prove that the interaction is not conservative? What say? affected the value, the surface area of my body affected the value of the drag force. Also, actually, the speed was affecting, but well, we would have to find out that the two works were different. Well, so far, if we recognize that they both are negative, I don't believe that they were different, right? Because in order to show that it is not conservative interaction, we will have to come to the conclusion that work was different when I walk in front of the screen only and when I walk behind of the screen. Well, unfortunately, in both cases, the only thing which we could say was that they were negative, but it doesn't implicate that they are different. Try to find out a path for which it will be obvious that the work was different. What do you mean, Mark, like that?
You just have more resistance, air resistance going down than you are going back up.
From air? Why? Mark suggests to move like that. And somehow I believe that it is also negative work. Ha! Don't move at all. Right? It is also a path. Yeah. So now I'm moving this way. I start and I end my motion. How much work was done now? 0. Right? So we found two different paths, and we figured out that the work was different. Therefore, we recognized that that interaction was non-conservative interaction. All right, so definitely we cannot move it to the side of mechanical energy. Now, when the bungee jumper jumps, the work performed on the person, this non-conservative work is going to be positive or negative? Negative, correct? Which means that what happens with the mechanical energy? It is going to decrease, right? So in reality, the jump is going to look like that. And look at the plots. Yes, so potential elastic potential energy obviously goes along the same line. Gravitational potential energy changes along the same line. However, kinetic energy, now if I add kinetic energy to those two, mechanical energy is going to decrease. So now when the person, oops, what does it want to say? All right. At this point, we can see that, well, the total potential energy is negative, kinetic energy is positive. The person lost mechanical energy because air performed negative work. Now, we have, so considering where the energy went, because energy is supposed to be conserved. Well, we have another type of energy which we'll discuss later in this semester, thermal energy. What the person did was to increase temperature of the air. That energy was converted and transferred as heat to air, increasing temperature of the atmosphere, which is actually not noticeable because it was a relatively small amount of energy, while atmosphere is pretty huge. You need a lot of energy to heat it up. All right. And now I promise that I'm going to pull your leg. So I decided to confuse you with something. I'm going to use now the law of conservation of energy to to figure out, well, this problem. Yeah, what should be the initial speed of an object which is supposed to escape to the gravitational field of the Earth? Yeah, so we can think about it, well, how fast this spacecraft should have when it is at the surface, so it will fly away from the Earth, so it will be moving, reach infinity. Now we can look at this problem actually from a different point of view as well, yeah, because I mean you can look at that if you are sitting in the spacecraft, you will see that Earth is flying away. So you could also look at this, how fast initially the Earth should move away from the spacecraft so that it goes into infinity. All right, now I will solve it in the reference frame of the Earth. So how fast the spacecraft has to move away from the Earth at the surface, what speed it should have at the surface so that it escapes far, far away. Obviously we cannot use the formula for the gravitational potential energy at the surface because the spacecraft is flying away further away than just being at the surface. So I will write down that, well, kinetic energy at the surface, so it is mass of the probe times speed, square of the speed which we are looking for, divided by 2. This would be kinetic energy. Gravitational potential energy at the surface with a reference at infinity is gravitational constant multiplied by mass of the Earth multiplied by mass of the spacecraft divided by the distance between the centers of the two objects, so it practically is the radius of Earth. Well, when it reaches infinity, it is sufficient that it will stop over there. It doesn't have to have kinetic energy at infinity, so I will assume that, well, that way I will find the minimum required escape speed. So I said that I set kinetic energy to be 0, far, far away, and potential energy at infinity is also 0. Why?
Because gravity no longer has an effect?
No, not because gravity has no effect, because it was our selection of the reference point to have this formula valid. We got that simple formula with a reference at infinity. So now when object is at infinity, its potential energy is 0. All right, so now I can check gravitational constant, mass of the Earth and radius of the Earth in the tables. I can recognize over here that mass of the probe and mass of the probe cancels. So I can find out the expression for escape speed from the Earth, and it's the value. Indeed, if we want to throw an object away from the Earth and make sure that it never comes back, this is how we have to how fast it has to move. 11.2 kilometers per second. By the way, do you remember how fast an object has to move in order to stay on the orbit? 7.9 kilometers per second. We were also doing solving this experiment, not experiment, calculation. All right. I'm going now to show you a different solution in the reference frame of the object. In other words, how fast the Earth has to move away in order to separate Earth and the probe. Obviously, the speed should be the same, right? Because if I move from JD 1 meter per second, how fast he's moving away from me? Also 1 meter per second. If I consider velocities, we have opposite velocities. So my velocity in his reference frame is opposite to his velocity in my reference frame. Do you see that? So I'm doing it now the same way. I see that Earth is supposed to escape now from the vicinity of the of the spacecraft. And I will use also a conservation of energy, this time for the Earth. So, kinetic energy of the Earth as it is flying away from the spacecraft is mass of the Earth times the same value of the escape speed squared divided by 2. Gravitation potential energy of the Earth, and I was going to follow exactly the same formula as before. And when Earth is far away, it is supposed to stop at least. It could have certain kinetic energy, but then it would mean that we gave too much energy at the very beginning. So in the most favorable case, it will just stop at infinity. And potential energy of the Earth far away is going to be 0. All right, so this time mass of the Earth cancels over here. And if I take a reasonable value for the mass of the spacecraft, I'll get that the escape speed is 1.5 times 10 to minus 7 meters per second. How come that it's not the same, and which one is correct? And why? I mean, because you probably know which one is correct. Which one is correct? The left-hand side, yeah, because if you look at this answer, you should immediately recognize that what? That it's unreasonable. Snails move faster than that. Right? And snails don't escape from the Earth. So definitely this answer is unreasonable. However, what's wrong in this solution? Talk to each other for a while. And don't check arithmetics, actually. Arithmetics is correct. Algebra is also correct. So don't try now to check if indeed from this expression I will get such an expression for escape speed. Something else, something more fundamental is wrong. What is it? And I advise you to check the work energy theorem. And if you don't see it in the work energy theorem, go to Newton's second law. Yes, Chris?
Discussing with a partner.
Oh, okay. Anybody has suggestion? Yes, Taylor. A shout.
The only thing I can see is that in the second reference frame, the mass is much smaller. It's the mass of the satellite.
Well, yes, and this is correct. Well, Taylor noticed that because this, so actually you verified that the answer is reasonable because this mass is much smaller than the mass of the Earth. So obviously this number should supposed to be much smaller as well. But this is not an argument against, right? It says that, well, this is the reason why that speed became so small. Yeah, we have another suggestion.
Isn't that the one we just calculated, the second one? What it takes for the Earth to escape the gravitational field of the satellite? But we're supposed to calculate
Yes,
the satellite.
yeah, correct. About what's the difference? Yes, so indeed. What's your name?
Brandon?
Brandon says that over here we had a problem in which the probe was escaping gravitational field of the Earth, which is true. And in this case, we were considering a case in which Earth was escaping gravitational field of the spacecraft, which is also true, but there's nothing wrong with that. Yes?
Are you trying to say that what's wrong is that we're not calculating the other object's gravitational pull?
No, we do.
Well,
In both cases, no, because with those fields, it is recognize that with those fields, we just divide the interaction into kind of two parts. Yeah, so instead of saying gravitational force exerted on the object, exerted second object by the first object, we say that the first object produces the field in which the second object is placed, and then because of that field, the force is exerted. So field itself is just an artificial concept which we introduced to eventually to calculate force anyway. So indeed, when we consider probe, why does it slow down? It slows down because of the gravitational force exerted by the Earth, which is true. Now, Newton's third law says that the spacecraft is pulling the Earth exactly with the same force of the same magnitude. So it's true. There is no error in the fact that in one case we were saying that the probe escapes gravitational field of the Earth, and in the second case Earth was escaping gravitational field of the probe. This is not the problem. This is still fine. Yes, Elena?
Can it only be in an inertial reference frame?
Aha! It has to be in an inertial reference frame. They both are actually not inertial. However, the reference frame of the Earth is more inertial than the reference frame of the spacecraft. That one is really bad. The reference frame of the spacecraft. Look now, take a look at Newton's second law in the reference frame of the spacecraft. Well, what is the net force exerted on the spacecraft in this situation? Let's think about free body diagram approximate, obviously, but identify significant forces exerted on the spacecraft. Gravitational force exerted by the Earth, correct? What else? Normal force exerted by drag? No. Normal force is exerted by what? Well, how? There is no normal force. Normal force is not exerted on the spacecraft. What else? Drag, right? Okay. Drag was exerted by? There is no air in space. So drag is not exerted. Okay. What else? What'd you say? Well, at the very beginning, at the surface, right? So when it is flying over there, there is no thrust anymore. Thrust existed only when we launched it. There is only gravity. I mean, on the test, don't put too many forces. Yeah, I bet that you will. Yeah, we have very few forces, and I mean, I know that we always think, well, the more forces we put, the better solution. It is not true. You have to give the right number of forces. All right, so there is only one force exerted on the spacecraft, gravitational force exerted on the spacecraft. Okay, now think about the forces exerted on the Earth in this system over here. Let's identify the forces exerted on the Earth. What exerts force on the Earth? Gravity does not exert the force. You mean that something exerts the gravitational force. What? The satellite, correct. The satellite. Compare the two forces. Compare the gravitational force exerted by the satellite on the Earth with the force exerted by the Earth on the satellite. Their magnitudes. Compare their magnitudes. Which one is greater? Earth exerts stronger force on the satellite, right? Why? Because it has greater mass. Now, what does Newton's third law say? That the magnitudes must be equal. No, so how come now that a greater mass results in the force which is greater, and it is supposed to be equal?
Because the Earth has a larger mass.
Yeah, because it has. Okay, how about if we write an expression for the force exerted by the Earth on the spacecraft? Which law should we use? Which one? No, not Newton's third law. Gravitational force. Universal law of gravitation, correct. So force exerted by the Earth on the spacecraft. So it is by Earth on spacecraft is gravitational constant, mass of the first object, mass of the second object, times the distance between the two objects, between the centers of these two objects, squared. This is magnitude of the force exerted by the Earth on the satellite. Let's figure out expression for the force exerted by the satellite on the Earth. It is gravitational constant, mass of the first object, mass of the second object, divided by the distance between the two objects. The distances happen to be the same. Gravitational constants are the same. Now this value is equal to this value is equal to that value. Which one is greater? Which one? Well, you were just saying that this one is greater. Universal law of gravitation and Newton's third law says that they are equal. The spacecraft pulls Earth with force of the same magnitude as the Earth pulls the spacecraft. Who believes that now? Who thinks still that Earth exerts a stronger force? I think I would kill you if you did that. I would spank. I mean, not that. No, this would be exaggeration. I would spank you. All right. So the magnitudes of the two forces are equal. Now, look what. Now, compare the net forces that exerted on both objects. On which object the magnitude of the net force is greater? Now, because I mean, for Earth we cannot find any more forces also. So gravitational force is going to be equal to the net force. So on which object the net force is going to be greater? Yes, Mark? They will be also the same. All right. So which object should have greater acceleration? The smaller one. The magnitude of acceleration of the smaller object should be greater. All right. In the reference frame of the spacecraft, which object has smaller mass? The spacecraft. Which means the spacecraft in an inertial reference frame should have a higher magnitude of acceleration than the Earth. All right, now, what is the acceleration of the spacecraft in the reference frame of the spacecraft? 0. How about Earth's? No, this is speed. Not 0, correct? So we see that the magnitude of acceleration of Earth is greater than magnitude of acceleration of the spacecraft in the reference frame of the spacecraft. Now, how about in the reference frame of the Earth? Acceleration of the spacecraft is greater in magnitude than acceleration of the Earth. Now, how many times actually acceleration of the spacecraft should be greater than acceleration of the Earth? Correct. Exactly like the ratio of the masses, right? Now divide mass of the spacecraft by mass of the Earth by mass of the spacecraft. Reasonable value. I mean, what's the reasonable value for mass of the spacecraft? Well, I mean, don't even think about it. How many times Earth is heavier than a spacecraft? A spacecraft probably has a mass of, well, less than all of us. So compare our mass with the mass of the Earth. What is our mass compared to the Earth? Negligible. Yeah, we can think that it's almost zero, or we can think that Earth has an infinite mass, right? Well, if we have an assumption that mass of the Earth is infinite compared to the mass of the spacecraft, then what would be acceleration of the Earth in the reference frame, in an inertial reference frame? Zero, correct. This is why we can, yeah, so actually Earth constitutes as good inertial reference frame as we can consider that mass of the Earth is infinite. Do you see that? Well, it is infinite if we compare with the spacecraft. Okay. I wanted. Oh, how about if I pull your leg tomorrow too? Because I have one more puzzle which I wanted to show you, but I think I'll do it. I'll do it tomorrow. All right. So this will be all for today then.